So the key things with the type of bonds are that there are three different types of bonds. One is your metallic bond, and that's between a metal and a metal. And that's basically done when you've got the metal, so basically sort of, if you like, abandon its electron. So the metal becomes the metal cation, and therefore it's surrounded.
Sorry, what of electron?
It gives it away, basically.
Oh, okay.
So it's surrounded. So it's not, but there's no one to give it away to, unlike what will come next. So it's therefore the electrons kind of just, go around.
Yeah.
So you've got the localized valence electrons. So basically, you've got your metal. All of these become cations.
So basically, oxidized is cations. So when you, okay, yeah.
And then these electrons then move around randomly. And that therefore allows you to form a metallic bond between the cations.
Yeah.
All right. 2 is your ionic bond that forms between a metal and a non-metal. And simplistically, your metal gives away an electron to the non-metal. So that means the metal becomes an M+ or some sort of cation. Could be get away too, that's possible as well. But the point is it gives it away. Whereas the non-metal accepts this electron and becomes a non-metal anion. A cation being positive, an anion being negative, means that there's this force of attraction, and that's your ionic bond.
Okay.
And simplistically, your third bond is called a covalent bond, typically formed between a non-metal and a non-metal. And that's when you've got a non-metal sharing an electron with another non-metal.
Yeah.
And that's when you might form a covalent bond, like so. So those are your three main types of bonds. Now, once you've got the type of bond down, you also need to realize that that gives you different types of substances or structures. So you've got ionic substances, which are made up of basically ions bound together by ionic bonds.
Yeah.
And these have all their properties, like, they're brittle, they're reasonably hard, they have moderately high boiling points, and, they are conductors in liquid form and aqueous form, but not solid.
Yeah.
All right. So that's a general idea for ionic substances. You also have metallic substances, which you can think of as metal cations, sort of bound together, bonded by metallic bonds. And then your typical properties are going to be they're ductile, malleable, moderate boiling points, moderate to high, depends on exactly which metal. And they're good conductors in their respective states. You've got your covalent network, which is mainly made up of atoms bonded by covalent bonds. So these have high or very high even extremely high boiling points and melting points. They are hard and brittle. And that's really the key thing here. They're very hard and they're very brittle. And you also have covalent molecular substances, which are really made up of molecules, sort of bonded together, sort of attracted, I wouldn't use the word bonded, attracted by intermolecular forces.
Yeah.
So you need to understand that the unit is different. The unit now is a molecule, no longer an atom or an ion or a cation. It's a molecule attracted by intermolecular forces. And these are typically soft. These are typically, low boiling point, melting point. These are poor conductors, and so on.
Yeah.
And those are your bonds in your different types. It's also important to know that these are the ones that have intermolecular forces, and therefore we need to consider, what type of intermolecular forces there are. But before we get there, we need to consider your bonds. Go back to your bonds. We said that, well, an ionic bond was when you basically, took an electron from another. And we said a covalent bond was when we shared an electron. So sharing is like a 50-50 sort of idea. And taking an electron is like, okay, well, I took it, so I have it 100% of the time and 0% of the time. But things are actually not that clear cut. These are what we call non-polar covalent bonds, otherwise known as pure covalent. An ionic bond is, if you like, when you basically don't share equally and you take it 100% of the time. But remember, a covalent bond is formed between two elements, so they both can pull on that electron. And so really, we look at the polarity of the bond, which depends on the difference in electronegativity between the elements. So basically, if the difference is 0 or very small, then think of it like a tug of war, right? Two elements are fighting for it. If they're just as strong as each other, it doesn't matter if they're both strong or if they're both weak, but if the difference is 0 or small, then it's just non-polar. If the difference is large, then it's going to be ionic. And then this is if the difference is moderate.
Yeah.
And that's where we have what's called a polar covalent bond. Now note that this is talking about a bond. You need to determine that the polarity of a molecule. So the polarity of a molecule depends on the polarity, if any, of the bonds within the molecule, as well as the geometry or shape of the molecule. So you need to both consider the molecules inside the molecule, the bonds in it, whether they are polar or not. And if they are polar, then the shape. So for example, something like HCl, chlorine is more electronegative, so it pulls. And so clearly this is a polar molecule, that's delta negative and that's delta positive. Something like carbon dioxide has this sort of shape. So it pulls to the left and this pulls to the right. So that's delta negative and delta negative, and this is delta positive. But because it's evenly pulled to the left and the right, while there are polar bonds, because you've got a left pole and a right pole, which cancel, the molecule is not polar. So you have to consider both, one, the polarity of the bonds, if any, and two, the geometry or shape of the molecule. Clearly, if you've got something like two atoms themselves, then this is clearly non-polar.
Yeah.
And if you have something like carbon and hydrogen, this is slightly polar, but often ignored, because in the context that you get it, often, you know, the hydrogen directions will cancel each other out most of the time anyway, and it's not strongly polar. So you need to firstly work out the polarity of the molecule. And the reason why you need to work out the polarity of the molecule is because you need to know if a molecule is polar or not to really determine the intermolecular forces between the molecules. And the intermolecular forces are important because it helps determine the physical properties of the of the molecule or substance. So, intermolecular forces are basically made up of different ones, depending on if you have a non-polar molecule, a polar molecule, or a, well, let me do it this way. So you've got three types of intermolecular forces. You've got dispersion, you've got dipole-dipole, and you've got hydrogen bonds. Now, dispersion is simple. Dispersion applies in all molecules.
Yeah.
So lots of people think dispersion only applies in non-polar molecules. That's not true. It is the only one that matters in a non-polar molecule, but it most certainly is not non-polar molecule only. So if you have a non-polar molecule, or a polar molecule for that matter, or a, you know, HC, HF, HN, HO, they all have dispersion forces.
Oh, okay.
Now, where the confusion I think people come up with is if you don't have a polar molecule, they do not have dipole-dipole and hydrogen bonds. So a non-polar molecule therefore has dispersion only. But that's not correct to say that dispersion only is for non-polar molecules. Dispersion occurs for all molecules. And that's because it relies on basically temporary dipoles, which all molecules would have.
So when you say H2F, does that mean just hydrogen and fluorine?
Yep, there's pretty much, yeah. All right, so dipole-dipole occurs for polar molecules, and HF, HO, and HON bonds normally result in a polar molecule, so these would have dipole-dipole forces. But generally, a polar molecule does not have a hydrogen bond. A dipole-dipole bond depends on, well, permanent dipoles. So this depends on temporary dipoles. And these depend on permanent dipoles, which is why it needs a polar molecule. And this basically needs a very, very polar bond, and that's why it requires your HO, HN, HF, because that's when the difference in electronegativity is large enough to cause an intermolecular force, you know, with a polarity strong enough to cause an intermolecular force with strong enough, but not so polar that we would call a polar bond. And that's why we need one of the least electronegative nonmetals, hydrogen, and one of the most electronegative nonmetals being, well, fluorine, nitrogen, and oxygen, and that gives you your hydrogen bond. Now, it's important to note that dispersion forces are proportional to well, simplified, their molecular mass or volume. Basically, the bigger the molecule and the heavier it is, the more electron it has, and so the stronger the dispersion force. So it's, you know, it's not 100% accurate to say dispersion forces are weak because it depends on the molecule. And that's why for the questions you get, that is, you know, they'll usually be for molecules of similar size, because once the size gets very different, the dispersion forces are quite different, and you can't really very well compare the size of the intermolecular force with each other.
Yeah.
Great. So make sure you are able to, basically whenever you are asked to talk about physical properties, okay, so rather than going through the properties themselves and explaining each and every one, just think of the technique. If you are trying to explain physical properties, you know, understand that it's a physical property, which then means you need to think of the sort of bonds in question. So you need to think of what substance it is. So what type of structure, which we covered earlier, one of those four. In that particular structure, what is the relevant bond? Is it covalent, ionic, metallic, or intermolecular force? And then you need to consider that bond, is that strong or weak? And if it's an intermolecular force, then you should think about what type of intermolecular force at this stage. You should be able to identify the type of intermolecular force. From that, does it take a lot of energy to break or disrupt? And that will therefore help you, for example, explain boiling point or melting point. If you're trying to explain other things like ductility and so on, then you kind of might sort of talk about the directionality of the bond versus the non-directional nature of a metallic bond, and so on. But physical properties ultimately relate to the bond between your particles, whereas your chemical properties relate to is ultimately your electron configuration.
Yep.
Now, there's a section on allotropes that we, you know, didn't really look at because it's less important at this point, but you can go and check that. But basically that is the same element, but different arrangements.
Arrangement of what?
Different bonding, basically.
Oh.
So you can look at carbon, so carbon, graphite, diamond. You can look at oxygen, ozone. You can look at, you know, your different types of phosphorus and so on.
Yeah.
But for now, we will now move on to review of the formulae of quantitative chemistry.